So we're kind of doing a quick version of it together so that we get more practice before the test. So we just kind of made like an executive decision. So the problems that we are going to graph now, okay, are going to be equations similar to these things here. And these are just a couple of examples of the way the graphs can look. So this kind of looks like a reciprocal function, right? It's not a reciprocal function because it has x in both the numerator and the denominator, okay? This one has multiple factors. It looks like a line, but it has a hole in it. I don't know, okay? This one, okay, looks, I don't know, it does this. These graphs can have crazy, crazy, crazy shapes, okay? And our job is to be able to look at the equation and know that it did something like that, okay? So this is going to be kind of like sketching our polynomials. There are some things that we're expected to know exactly, and then some things where we're like, well, it's supposed to do this, it could be like this, but there could be some varying in there, okay? And so all of these are going to be this fraction form where you're going to see x's in the numerator and denominator. So does everybody understand the difference between the graphing procedure we're about to look at and what we looked at yesterday? Yesterday's function was a lot simpler. It was a number on top of like an x minus h kind of thing, right? These got like x's everywhere, okay? That's what's happening here, okay? So, all right. So here are a group of example equations that technically we could graph, okay? We're not gonna graph anything as crazy as this right here, all right? So I grouped these equations together because they have a specific relationship. So I specifically want you to look at the degrees of the polynomials in these fractions, okay? What could you say is true about all four of these equations when you look at the degrees of the polynomials in their fractions? Taylor? Okay, so they're all written in standard form. They go from greatest to least, right? Okay. What's the degree of this polynomial up here in the numerator of this j function? 4. And what's the degree of its denominator? 3. Okay. In the h function, what's the degree of the numerator? 2. And the degree of the denominator? 1. Okay, when you look at that for each of these functions, what's one kind of blanket statement we could say about that comparison? These functions all are written in a way that what's true about what we're talking about, all right? Good. The degree in the numerator is greater than the degree of the denominator. Is that okay with everybody? Okay, so that's why I grouped these ones together. And then we're going to look at their graphs. It's going to be a little bit weird. All right. Oh, sorry. I need to zoom out. Zoom, stop. There we go. Okay. So some of them look like lines. One of them looks kind of like a parabola, okay? But what I want you to look at is the ends of these functions, okay? Let's say we look at this blue one that looks like a parabola, right? The left end goes towards negative infinity. The right end goes towards negative infinity. Let's look at this like orange one, right? The right end goes towards negative infinity. The left end goes towards positive infinity. Okay, the green one is a lot slower than the other ones, but it's still slanted like a line. The left end goes towards negative infinity, and the right end goes towards positive infinity. So these functions were grouped together because that degree was higher in the numerator than in the denominator. And what that means is when you put all of these functions on a graph, you know nothing else about them right now. We'll work on that in a minute. But you do know that the ends of them either go towards infinity or negative infinity. Is that okay with everybody? So if the higher degree is in the numerator, the ends are going towards infinity or negative infinity. Which one? Are they the same? No idea. Are we just okay with, like, in that case, this is what happens? Okay. All right. So let's look at a different group of equations. Sorry, we're skipping all this. See? All right, second group of equations. Look at them the same way we looked at the last group of equations, okay? What do you notice about degrees here in these fractions? So in the last group, the degree of the numerator was higher than the degree of the denominator, okay? What do we see here? Dylan? They're the same. Is everybody okay with that? In each function, the numerator and denominator have the same highest power on x, okay? So we graphed these. We'll show you guys what these looked like when we graphed them. Okay, they look pretty crazy, okay? So I'll turn them off for you so we can look at one at a time if that helps. All right, so here's the red one. Its left end, is it going towards infinity or negative infinity? No, instead it's looking horizontal, right? And it's looking like it's horizontal at about, I don't know, that's 10, 2, 4, 6, no, 3, 6, 9, no. Oh, so that's 5, that's 2.5, right? Like maybe 2? Okay, you guys already said that. It takes me a minute. All right, so like maybe like 2 it looks like it's at, okay? And then look at the right end. It's not going towards infinity or negative infinity either. It kind of looks more maybe like 2.5. I'd probably have to zoom out a little bit to see if it's sitting at 2 or 2.5. But do you see that the ends don't go towards infinity or negative infinity? They kind of stay horizontal, very close to one number like we saw yesterday in our reciprocal function, okay? And then I'll turn on a different one. So here's the blue one. It's crazy. It's got like 3 branches, like something happening here, something happening here, something happening here. But if I look only at the ends, the left end seems to get very close to 0, right, like the axis. And the right end seems to get very close to 0, like the axis. So again, it's horizontal. Maybe that one's at 0, maybe not. I'd probably have to zoom in a little more to see as well. Okay. Here's the green one. It's like the blue one. It's got like 3 things going on. Again, see how the ends are horizontal? Okay, looking. And then here's the orange one, okay? A little bit different. I don't know what's happening there, okay? But a little bit different, but again, the ends are horizontal. Is that okay with everybody? So right now, when we see the degrees that are higher in the numerator, we think the ends either go off to infinity or negative infinity. We don't know which one, but something like that. When the degrees are the same, they hover around some number. And we'll come back to these and try to figure out the number. Or you know what? Let's look at it right now. Okay, so let's look at the orange one. I'm going to zoom it in a little bit so we can see more which number it's like hovering around. Okay, or I can like, yeah, get some points here. So 3.5, 3.6. Actually, I have something else that might help us. You're going to hate it, but. All right, here's the first function up there that I called f. Here's me plugging in a bunch of x's, like 0 in the middle, and then I got bigger and bigger and bigger, like 1, 10, 100, 1,000, 10,000, okay? Notice at first it's kind of like all over the place, but then notice what happens. 2.5, 2.056, 2.0057. If I plug in an even bigger number, notice that this number is starting to just hover right around 2, okay? And that's like what we saw on the first one. And the other way, it looks a little different, 1.45, 1.94, 1.994 something, but then I'd expect the next one to maybe be like 1.9999. It seems to be developing more 9s, which means it's getting very, very close to being 2, okay? So see how we can determine with the numbers also instead of looking at the graph that it's hovering around 2? Okay, so look at the equations. So this first one seems to be hovering around 2. This one, so look, 0.192, 0.194, 0.199. What do you think it's going towards? If this pattern continued, I would expect like a 0.1999. Like see how the more 9s are, but there's a 1 first, right? 0.1999999, which you guys would round to mean 0.2, okay? Just as a note, stare at the fraction for a minute, right here. 0.2 in fraction form is the same as 1/5. Okay? All right. This one, negative 0.32, negative 0.3339, negative 0.3334. Okay? So to me, when I look at that pattern, it's just developing more 3s after the decimal. Okay? What is a number that repeats 3s forever after the decimal? 1/3. So this is looking like negative 1/3. Okay? Look at the fraction for a minute, okay? This one goes to negative 1/3. And then this one, 3.4, 3.94, 3.994. So I would expect it to be like 3.999999, which means it's basically getting very close to being 4. Look at the fraction, okay? This one's getting very close to being 4. Does anybody have any idea, so that you would not have to do what I had to do right here, because we don't want to have to plug in lots of numbers to these crazy things, how we could look here? So we already know we could look here and say, oh, same degree. They're going to be at a number at the ends. They're going to be flat at one number, okay? Now, can you look at it and be like, I know the number it's going to be flat at, okay? Does anybody have any idea? So look just at these. This one was at 2. This one was at 1/5. This one was at negative 1/3. This one was at 4. Okay, Noel?
Like for any of them, when they have the same degrees, so for the first one, when you divide the coefficients, that would be 2. And then say for the next one, that's 1/5. And then that one's 3 x squared, and then that becomes 1/3. And then same with the last one, which becomes 1.
So what she said is look at them and look at the lead coefficients if it was written in standard form, like that piece with the highest power, right? So the highest power here is 12x and 6x. 12 divided by 6 is 2, and this one approached 2. Okay? Here, 1 divided by 5 is 1/5 or 0.2, and that's what this one approached. Here, it's not written right, but the lead coefficient would be -3. -3 over 9 is the same as -1/3 or -0.3 repeating. And here, 8 over 2 is 4. So when they're the same degree, we know they're not going to go towards infinity. They're going to flatten out a number, and we can use the lead coefficients to figure out what that number is without plugging anything in. Is that okay with everybody? All right. So there's one more category. Any ideas what the next category of equations is going to be? So we've seen ones with higher degree in the numerator. Their ends go off to infinity somewhere. Okay, Jake?
Lower degree.
Yeah, so what happens when we put the lower degree in the numerator and it's the denominator that has the higher degree? So take a look at these functions. Can you guys all see that the denominator has the higher degree? Okay, and so here's what these guys look like on a graph. So I'll turn these off again so we can look at one at a time. All right, so again, the ends look what? Like they're horizontal, right? Okay, so this has something in common with that middle category where they had the same, all right? So here's the first function. They look horizontal and they look like they're going towards 0, maybe. Here's the next one. So it has a crazy thing in the middle, but again, looks like it's at 0. Here's the third one, okay? Couple of branches, but again, looks like it settles down horizontally at 0. And then here's the last one, okay? So these ones are like the last category in that the ends are horizontal, but all of these ends ended up where? You know how in the last one we had some at 2, some at 4. Where did all of these ends appear to be going? At 0, okay? So in this case, not only do you know it's horizontal, you just automatically know it's at 0. So if the higher degree is in the denominator, it's at 0. Is that okay with everybody? Okay. So what we're going to try and develop here is that we can look at an equation and we have a bunch of tools that we can figure out. We already have the tools to figure out the rest of the info. I'll talk about it in a minute. But we wanted to develop in here a tool to understand what the ends are doing. Because if we're going to sketch this graph and we get a few different points, you saw how crazy they look. I'm not really going to know where they go. So we're going to try and use like the boundaries and the asymptotes and things to help us know where it's split up and stuff like this. And we need this to know how to draw the ends of the graph. Like, oh, do I draw it flat? Do I draw it towards infinity? Do I draw it towards negative infinity? Okay. And so this is kind of helping us when we look at the original equation to at least know which category it falls in and to know, do I expect it to be at 0? Do I expect it to be at some other number? Or do I expect it to go towards infinity or negative infinity at the ends? Okay. So in your note guide, you have a place for these conclusions. If you don't have the note guide, that's totally fine. You just put these conclusions where your notes are. So the note guide has the same picture that this investigation started with, just to give you some examples of how these functions are built and what they could look like. And then these are like the 3 conclusions that we came up with, okay? So first category, right, was if the degree of the numerator was greater than the degree of the denominator. And just give yourself an example. Just make sure, in case you forgot what degree is, that you understand that's like maybe having like a cubic up here and something that's of lower degree down here, okay? And then my question is there a horizontal asymptote? So remember from yesterday, a horizontal asymptote was to say that your ends become horizontal. In that first category, did the ends become horizontal? No, they went towards infinity and negative infinity. So this would have no horizontal asymptote. So how do you find it? You don't, okay? But it does have something else, okay? You actually have to find an oblique asymptote. So oblique is just kind of another word for slanted. Because you know how we said, well, they go towards infinity or negative infinity, but we kind of didn't know how we'd know. Like, does it go up? Does it go down? Do they go together? Do they go opposite ways? We'll follow something else that's not horizontal. So maybe we'll follow a slanted line, and then we'll know that that end goes up and this end goes down, depending on the slope or something like that, okay? So if the degree is greater in the numerator, there's no horizontal asymptote, and instead you're gonna find a slanted kind of asymptote to know which end goes towards infinity or negative infinity or what, okay? If the second category, if the degree of the numerator is the same as or equal to, will probably be, so the same as or equal to the degree of the denominator. And so again, just give yourself any quick example. It doesn't matter. I just want to make sure you guys understand what degree is, okay? In that case, was there a horizontal asymptote? So did the ends become like a horizontal line? Yes, okay? And then we had to look really close at the numbers, and how did we figure out how to find this? Okay. Somebody summarize what Noelle told us earlier. Let's say that this was the equation I gave you. You know that it's horizontal. Can somebody tell me what number that horizontal asymptote is going to be at? Dominic?
Divide the coefficients that have equal degree.
Good. Okay. You use the lead coefficients. So for example, in my example, that would be my polynomials have degree 2 in the fraction. The 1 and the 2 would be the lead coefficients. And so my asymptote, horizontal asymptote, would be at 1/2. Okay. Now, can you cross a horizontal asymptote? You saw those graphs. They're crazy, right? In the middle, when they were like breaking apart and doing all these things, is it possible they crossed that horizontal line? Yeah. What is the only reason that we want the horizontal line there? What's the only reason I want to know this 1/2? Where did the graph behave like this? Where did the graph start to look like 1/2 or 0 or whatever else we saw was a horizontal line? In the middle, did it look like that? No, it was like breaking apart, doing crazy things. It started to look like this at the ends of the graph. So you guys really want to remind yourself these horizontal asymptotes are only to mark for yourself the ends. Crazy things can happen in the middle. These are just to guide the ends of your graph because we don't want to plug in points. Do you guys want to plug in points to the crazy equations that we've been working with? Like I don't, okay? So I just want to know where it's supposed to go at the end. All right, last category was the degree of the numerator is less than the degree of the denominator. So maybe something like that. That also had a horizontal asymptote, okay? And where was the horizontal asymptote in all of those equations, though they were different in that category? It was at 0 for all of them. So this is like the simplest one, I guess, category. Maybe you hope for that because you don't really have to do any work. So if you see one like this, you say, I know it has a horizontal asymptote and I already know that it's at 0. You see one like this, okay, same degrees. You say, I know there's a horizontal asymptote. Let me look at the numbers and figure out where it is. 1/2, okay? you see one like this, greater degree in the numerator, and you say, darn it, there is no horizontal asymptote. These ends go off to infinity, so I won't have something horizontal guiding my ends. I will have something else guiding my ends, and we'll get used to this vocabulary. We call it an oblique asymptote. Some textbooks call it like a slant asymptote because it's literally just usually like a line that has a slope instead of a horizontal line. Okay? Is this all right with everybody? Okay, so then I want to take a quick look. If you don't have the note guide, you're going to think this is crazy. If you want to see me, I'll print out this one page for you at a different point in time. It just has a lot of information on it for you. So here's the deal. We want to find all of these things about our functions. When we look at these crazy things, we don't want to plug in points. How are we going to know what the heck is happening there, okay? So the first thing we would focus on are asymptotes, okay? Horizontal asymptotes we just talked about. I'm going to write, see the chart above, because that is based on degree, right? So horizontal asymptotes are complicated. We have to like analyze the degree very deeply to understand which category we're in. And then notice I gave you guys keywords here. Horizontal asymptotes are for end behavior, meaning can I cross them? Yes, they are only there to guide the ends of my graph, okay? Notice that the oblique asymptote also says end behavior. Because if you don't have a horizontal asymptote, you have an oblique asymptote, okay? And we'll go through this a little bit more tomorrow when we do an example. We are going to use division to find oblique asymptotes. Like we're actually going to take the crazy fraction and do what we learned last unit, and we're going to perform the actual division problem and see what the answer to the division problem is, because that's just a different way to write the problem they gave you, and that will give us an idea of how slanted it is. Like, is it really steep? Is it not so steep? And we'll look at those things, okay? The third type of asymptote that we can have is a vertical asymptote. We talked about these yesterday, okay? They are specifically when the function is undefined, okay? And when is a fraction undefined? When there's a 0 in the denominator. So how are we going to find our vertical asymptotes? We are going to set the denominator equal to 0 and then solve for x. And we'll get x equals one value, maybe two values, maybe three values, depending on how many different x's can make the denominator equal to 0. Remember our restrictions that we worked on since the beginning? Those things will determine our vertical asymptote, okay? They have another weird name I'm going to show you. You're going to think it's kind of weird. Okay, this part shouldn't be that weird. I mean, maybe a new word, but it's a discontinuity, okay? So remember when we were doing piecewise graphs, we asked you guys, is the graph continuous or not continuous or discontinuous, okay? That meant you could put your pencil on the whole thing. Rational functions sometimes get split into branches, right? If they get split into more than one branch, then they are not continuous. So that's why a vertical asymptote is called a discontinuity, because it's the thing that splits up the graph. Is that okay with everybody? Why is it called non-removable? Because there's two ways to split up your graph. You can split your graph with an entire barrier, or remember the picture we saw at the beginning that was like a line with a hole in it? That's another way to split the graph. So I'm going to go down to holes real quick. Notice that if we have a hole in our graph, it's also called a discontinuity. That should make sense in one sense because it's making the graph split apart, like it's jumping over a point. But notice that this one is called removable. So vertical asymptote's not removable. This one is removable. What the heck do they mean by that? They're talking about the way that algebra is set up. So here's how you're going to know if there's a hole in your problem. Let's say that I gave you guys this equation and I wanted you to graph it. Before we graphed it, we would try to simplify it if we could, right? And this one does factor in the numerator. And then look what happens. X plus 2 just cancels out, and we end up with an equation that says y equals x minus 2. What kind of shape is x minus 2 if you graph that on a graph? It's just a line, right? It's a line. But it's a little bit tricky. Can you plug negative 2 into your new equation right here for x? Sure, I plug in negative 2. Negative 2 minus 2 is 4, okay? These are supposed to be the same thing, right? This is just a new version of that thing because I simplified it. Yeah, plug negative 2 into this original thing. Negative 2 squared is 4. 4 minus 4 is 0. Divided by negative 2 plus 2, which is 0. What is 0 divided by 0? Is it? Is it 5? Is it 8? We don't know either. It's okay to not know. I don't know either. Okay? But the problem is that's undefined. So this is supposed to be a simpler version of that. And it is, except for in one tiny instance, right? There's one problem where they don't actually match up, and that's at the number negative 2 that comes from the thing that I canceled out. So if I can cancel out a denominator, if I can remove a factor from the equation, get it? Removable discontinuity. It got removed from the equation. It's causing a hole. So when you can do this, this is causing a hole. Okay? Where is the hole at? Take the thing that you factored out and set it equal to 0. You get the x value, and then you see what that would be in this equation here that's like tricking you. So you plug it in. Negative 2 minus 2 is negative 4. My graph has a hole at that equation. So this is how you get the graph of a line with a hole in it. Is that this is a line, but because I'm supposed to be graphing this, it doesn't really work for this one thing that they plugged in. So I have to like remove that one point from the line because it doesn't actually work. So that's a removable discontinuity. The vertical asymptote doesn't get canceled out of the equation, right? It's just when the denominators equal 0. So it's a non-removable discontinuity, if that helps you with the complication of the names, okay? All right, the other things that we're going to find in this list are x-intercepts and y-intercepts. We follow the same procedure that we always have. We just know the solving and the calculating might be a little more complicated because our equation's a little more complicated. So for x-intercepts, you're going to set y equal to 0 and then solve for x. And remember, an x-intercept is a point. This will be very important to you here because for every time we try to graph one of these, we're going to collect this entire list of information. This is our only hope, right? We're not going to randomly plug in points. You saw those crazy shapes. How would I ever know, right? This information is supposed to help us generally understand how many times it's broken up. Where do the ends go? Does it cross the x-axis? Does it cross the y-axis? So we're always going to collect this information first, okay? So you want to write your intercepts as points. Because if you just write numbers or you write like x equals 5, do you see how writing x equals 5 might confuse you with your vertical asymptote or something like that? So we're going to write our asymptotes as equations, our intercepts as points to help us understand how to put them on the graph. And for our y-intercept, we'll set x equal to 0 and solve for y. And remember, that's giving us a point that looks something like this. So you can, if you want, I'm going to give you guys the cushion here. I'll kind of tell you what you're going to have. So